Right now, the absolute smartest brains on the planet are, well, they're completely paralyzed.
Yeah, that's actually a really good way to put it.
I mean, they can write complex code, they can, diagnose rare diseases, instantly translate dead languages, all of it. But they can't do a single one of those things unless they are permanently chained to a billion-dollar energy-guzzling data center.
Right. It's like you might imagine modern AI as this omnipresent digital cloud floating around everywhere, but the reality is much more rigid than that.
Exactly. It requires these massive warehouse-sized servers,
Uh-huh.
specialized accelerators, and a continuous internet connection. It's brilliant, yes, but fundamentally trapped.
Trapped is the perfect word for it. And that physical dependency, it restricts absolutely everything. I mean, it limits affordable access for smaller organizations. It destroys user privacy because, your personal data has to travel back and forth over a network. And it makes low latency or offline use basically impossible.
Yeah, you can't exactly put a server farm inside a pacemaker.
No, you definitely can't. Or a remote agricultural drone, right?
Yeah. Right. Like if you are off the grid or if you're a hospital needing instant private analysis on a local device without sending patient data to a third party, well, that cloud-tethered brain doesn't do you much good at all.
Exactly.
And overcoming that specific limitation is the entire mission of today's deep dive. We are looking at this highly technical, frankly fascinating set of living research documents and experiment logs,
Yeah, they detail a project called Teacher-Healed Quantization.
which sounds very sci-fi, but we'll get into it.
It does. But these documents, they really represent a forensic operational blueprint. The core objective the researchers are tackling is how to shrink a massive, high-performing AI model down so it can run efficiently on regular, everyday hardware.
Right, what the industry calls the edge.
Exactly, the
But the trick, and this is the hard part, is doing that without giving the AI severe brain damage in the process. Okay, let's unpack this. Because before we dive into this new teacher-healed solution, we really have to understand why it is so incredibly difficult to shrink an AI in the first place.
Right, and the researchers outline this problem by comparing what they call the research gap to true deployment reality.
So what exactly is this research gap?
Well, the research gap is essentially this massive industry-wide blind spot. Usually, when academics try to compress a model, they focus entirely on theoretical metrics.
Like what kind of metrics?
They look at parameter counts or theoretical FLOPs, which stands for floating point operations per second.
Okay, so just a measure of raw mathematical operation.
Right. And they look at something called top one clean accuracy.
In other words, did the AI get the exact right answer in a perfectly sterile, pristine laboratory test?
Exactly. But laboratory conditions do not reflect true deployment reality at all.
Because the real world is messy.
Extremely messy. Deploying an AI onto a smartwatch or, I don't know, a factory robotics arm, a local medical scanner, that relies on entirely different constraints. Theoretical math doesn't matter if your battery drains in 5 minutes.
That makes sense.
Right, so true deployment reality means measuring median latency, sure, but more importantly, 95th percentile tail latency.
Meaning the absolute worst case scenario delays.
Yes, exactly.
So it's not just about how fast the AI responds most of the time. It's about whether it randomly hangs for 3 seconds when a self-driving car needs to, hit the brakes.
Which is life or death. And you have to add to that peak RAM and VRAM usage, actual measured energy consumption, and failure consistency.
Right.
The documents argue that standard research just completely ignores these physical hardware realities in favor of, nice-looking theoretical numbers on a whiteboard.
I mean, it reminds me of taking a high-performance sports car and just deciding to make the engine smaller.
Okay, I like this.
Like, sure, you chop it in half, it weighs less, it's physically smaller. But if that new tiny engine now requires some impossible-to-find fuel type to actually run, or it stalls every time you hit 40 miles an hour, you haven't actually made the car more drivable.
Right, you just broke it in a different way.
Exactly. Standard AI compression seems to do the same thing. A compressed model might become smaller on your hard drive, but if it now runs terribly slow on the actual hardware you own, you haven't improved anything.
What's fascinating here is that the researchers explicitly state that theoretical compression gains are utterly invalid unless they are verified on actual specified hardware. They completely refuse to deal in hypotheticals.
They actually name the hardware, right?
Oh, yeah. For their baseline tests, they're running everything on an AWS EC2 G4DN.X large instance using a specific NVIDIA Tesla T4 GPU.
That is very specific.
It has to be. They note that a poorly compressed model might actually retain its average clean accuracy like. It might still get 90% of the questions right, but completely lose its reliability on that hardware. It becomes uncalibrated.
Okay, wait, uncalibrated. Let's break that down for a second because it's a huge theme in these documents.
It really is.
An uncalibrated AI is basically one that acts highly confident even when it is completely wildly wrong, which is, terrifying if that AI is making a medical diagnosis or flying a drone. You do not want a system that is confidently wrong.
It's arguably the most dangerous kind of failure.
Yeah,
So we know standard compression often breaks the model's reliability and calibration.
right. So if standard compression is so deeply flawed, how are these researchers proposing we actually fix it?
Well, they present this two-step solution in the logs, which they call the double
What's
intervention.
an intervention? Okay.
Step 1 is quantization, and step 2 is the teacher healing process. Let's start with step 1, the mechanism of quantization itself.
Let's do it.
So the central hypothesis starts with the dense FP32 model. FP32 stands for 32-bit floating point precision.
Okay.
Just imagine a number with dozens of decimal places.
Yeah.
It is mathematically highly accurate, which allows for these incredibly subtle gradients in the AI's decision-making process. But, and this is the catch, it requires a massive amount of memory and compute to process.
So it's smart but heavy.
Exactly. So the primary intervention quantization takes that complex math and forcefully shrinks it down into an INT8 format.
INT8 being an 8-bit integer. So we are taking those long, complex decimals and basically just rounding them off to whole numbers.
Yeah, you're chopping the precision down to a quarter of its original size. Mathematically, it's a pretty brutal process.
It's like translating a really gorgeous, nuanced, epic poem into a language that only has a 100-word dictionary.
Oh, that's a great analogy.
Like, standard compression approaches the problem by just deleting the complex words to save space. Sure, the dictionary is smaller, it takes up less memory, but you lose all the subtle emotional context, the nuance, the model gets fuzzy.
Right. It suffers from what they call quantization-induced capability loss.
Okay, and that capability loss is where step 2 comes in, right?
Yes. The secondary intervention, teacher healing. So the researchers in this specific experiment are using a ResNet 18 architecture as the student model.
Meaning the smaller one they just compressed.
Exactly. And to heal the damage caused by that INT8 conversion, they bring in a much larger, highly capable, full-precision ResNet 50 model to act as the teacher.
Okay, wait, hold on. Let me play devil's advocate for a second here.
Go for it.
Isn't teacher healing just a really fancy, marketing-heavy rebrand for fine-tuning a broken model? I mean, the industry has been doing knowledge distillation for years.
True.
You take a big model, you use it to train a small model. What is mechanically different about calling it healing?
I get why you'd ask that.
Yeah.
But if we connect this to the bigger picture, the distinction is entirely about the rigorous filtering of the supervision. The documents actually include a strict method control rule in bold text that absolutely forbids using teacher healing as a label for generic retraining or vanilla knowledge distillation.
Oh, really? They actually forbid it?
Yeah, they're very serious about it. In standard knowledge distillation, the teacher model transfers all of its raw outputs, which are called logits,
Yeah.
directly to the student.
So it just dumps its entire brain into the student, including all of its, bad guesses or moments of confusion.
Precisely the problem.
Hmm.
If the massive teacher model is uncalibrated on a specific edge case, or if it makes a low-confidence, sloppy guess on a highly distorted image, it forces the student to learn that sloppy guess.
It's like a professor teaching a student a complicated math equation, getting it wrong themselves, and then forcing the student to memorize the wrong answer.
Yes, and teacher healing prevents this by placing specific filter gates between the two models.
Right. The documents specifically mention 2 gates, I think, a calibration gate and a confidence-aware gate. Let's explain how those actually work under the hood.
So the calibration gate utilizes something called temperature scaling.
Which sounds like a thermostat for a server room, but it's actually purely mathematical, right?
It is. Think of temperature scaling as a way to soften the arrogance of the teacher model. If the teacher looks at a blurry image and says, I am 99.9% sure this is a dog and 0.1% sure it is a cat, but it's actually a cat, that extreme overconfidence damages the student.
Right.
So temperature scaling smooths out that probability distribution. It might adjust those logic to say, I'm 80% sure it's a dog, but there's a 20% chance it's a cat. It makes the teacher's knowledge transfer far more nuanced and calibrated.
Ah, so it forces the teacher to admit a level of doubt, which is actually way more useful for the student to learn from than blind overconfidence.
Exactly. And then there's the second gate, the confidence-aware gate.
How does that one work?
This one is more of a hard filter. It actively monitors the supervision. If the teacher model is highly confident and calibrated, the gate lets the knowledge pass through to the student.
Makes sense.
But if the teacher's supervision on a specific piece of data falls below a certain reliability threshold, the gate just slams shut,
That blocks it completely.
blocks it entirely, and replaces it with the actual verified ground truth data from the data set.
Wow, okay. So the teacher is only allowed to speak when it actually knows what it's talking about. It's like a highly curated tutoring session. That makes total sense.
Yes, it's brilliant.
But if this teacher healing process is designed to balance all this capability with the much smaller INT8 footprint, how do the researchers mathematically prove it actually worked? I mean, they can't just say, well, it feels smarter now.
No, they cannot. And they've developed an incredibly strict mathematical framework just to judge their own success.
Right.
The primary decision metric they use is an entirely new composite score called CPEDF.
Capability per effective deployment footprint.
That's the one.
Let's break down this ultimate scorecard because the formulas they use for this are intense. Higher values basically mean you are preserving more capability for every single unit of deployment burden on the hardware.
Right, so we have to look at the numerator first, the capability score. Standard AI research usually just looks at clean accuracy, but here, clean accuracy is only weighted at 0.45 or 45% of the score.
Which is a massive departure from standard AI benchmarks where accuracy is treated as, like, the only thing that matters.
Exactly. It forces a much more holistic view of the AI. The rest of the capability score is made up of a 0.25 weight for corruption robustness.
Meaning, how well does the AI handle messy, real-world data like a camera lens smeared with grease or a microphone picking up background wind?
Yes. And then there's a 0.15 weight for something called 1 minus ECE. ECE stands for expected calibration error.
So they're mathematically rewarding the model for knowing when it is confused.
It goes back to our discussion about the dangerous, overconfident AI. A high expected calibration error means the model is frequently confident and wrong.
Like a terrible driver who is 100% certain they know a shortcut but gets you lost half the time.
Exactly. By heavily weighting 1 minus ECE, they demand the model possess a high degree of self-awareness about its own limitations.
Okay, so that leaves another 15%.
Right. Finally, there's a 0.15 weight for failure consistency.
Meaning, if the teacher model failed on a specific blurry image, does the compressed student model fail in the exact same predictable way? Or does it fail randomly, introducing new chaotic errors?
Exactly. You want predictable failures. So that's the capability side. Then there is the denominator, the EDF score.
The effective deployment footprint.
Right. And the footprint is equally balanced across 4 real-world deployment constraints. 0.25 for serialized size, literally how much disk space it takes up.
Okay.
0.25 for peak memory, how much VRAM it spikes during operation. 0.25 for measured latency, how fast it processes, and 0.25 for energy consumption.
Okay, here's where it gets really interesting, and frankly a little concerning to me.
Oh.
Yeah, whenever you mash a bunch of disparate metrics like accuracy, memory, energy, calibration into one single composite score like CPEDF, aren't you just creating a brilliant way to hide terrible performance in one specific area?
That is a very valid concern.
Yep. I mean, think about it. What if the quantized model is incredibly energy efficient and tiny, so the footprint denominator looks fantastic, but its failure consistency is completely falling apart? You could totally mask a fatal flaw behind a high overall CPEDF score.
Yeah, that is a very real danger in data science.
Mm-hmm.
It's known as aggregate masking. But the researchers anticipated this exact vulnerability.
Oh, they did?
Yes. To prevent it, they established a strict masking guardrail mandate within a broader qualitative framework they call MIRACLE.
Right. MIRACLE stands for Method Interpretation, Impact, Risk and Integrity, Context, Learning, Evolution, and Limitations.
Exactly. And as part of the risk and integrity pillar of MIRACLE, the protocol strictly dictates that the CPEDF composite score can never, ever be published alone.
So they have to show their work.
Oh, absolutely. The raw underlying metrics must always be published right beside it. They are mandated to show the full Pareto frontiers, negative log likelihood, and macro F1 scores.
Okay, for those who might not spend their weekends reading data science textbooks, let me explain why macro F1 is a crucial metric here. Please do.
If an AI looks at a medical data set of 99 healthy patients and 1 sick patient, and the AI just blindly guesses healthy every single time, its standard accuracy is 99%.
Right.
It looks like a genius. But a macro F1 score takes the harmonic mean of precision and recall for every category equally. It would immediately expose that the AI failed completely on the minority class, the sick patient.
Exactly. By mandating the publication of macro F1 and negative log likelihood, the researchers are building a glass house for their own data. They are forcing themselves to show the unvarnished reality of the model's performance, completely preventing any single broken metric from hiding behind an aggregate average.
They cannot hide. And honestly, we need to look at the current status of this project because reading these living documents feels less like reviewing a standard research paper and more like watching a forensic audit.
It really does.
We are looking at live experiment logs, and the level of paranoid control they are enforcing over their own environment is just staggering. It is incredibly rigorous. Right now, according to the logs dated July 28, 2026, the project is officially locked at what they designate as Gate G1.
Locked, meaning all forward progress is completely halted.
Yes, they have established their initial FP32 baseline, but the documents explicitly state that the INTA quantization step is strictly unauthorized until the full effective deployment footprint measurement protocol is completely frozen and verified.
Wow.
They absolutely refuse to run the experiments until their baseline is mathematically unassailable.
And there was some serious internal drama just trying to get that baseline locked down. If you look at the logs for their baseline model, which is CNN0002BE0, they ended up with two different checkpoints fighting for the top spot.
Right.
There was a best checkpoint, which had a cryptographic SHA-256 hash ending in 5e36, and a final checkpoint.
And honestly, the mere fact that they're tracking file integrity down to a cryptographic SHA-256 hash tells you everything you need to know about their methodology. They don't trust file names.
Not at all.
No, they trust the mathematical fingerprint of the file.
Yeah.
So they ran a deterministic head-to-head evaluation of both checkpoints using a 10,000 image test split from the CR10 dataset.
Right. And they officially selected the best checkpoint, the one ending in 5e36, because it hit a 93.81% accuracy and a 0.9381 macro F1 score, just narrowly beating the final checkpoint, which hit 93.70%.
Yeah, but they didn't just log the accuracy, they verified the exact parameter count.
Yes, exactly. 11,173,962 parameters.
Right.
Not an estimate of 11 million, that exact single-digit number.
Yes, 11,173,962.
Wait, they're counting over 11 million parameters down to the single digit? That is obsessive.
It really is.
I mean, if even one parameter is off, if a future run accidentally creates 11,173,963 parameters because of a slightly different input convolution, they just throw the whole thing out.
Immediately, it is flagged as a provenance mismatch and discarded. It ensures that any gains or losses in performance are solely due to their teacher healing method, not some random architectural drift.
It's intense. And my absolute favorite part of these logs is the critical bug they caught during what they call the E1 PTQ preflight.
Oh, that was wild.
They were attempting to do the initial software conversion from the FP32 model to the INT8 quantized model, and the entire process just crashed.
But the crash had absolutely nothing to do with the AI model itself or the mathematics of quantization.
Never.
It was a pure environmental software bug. Their main processing environment was running specific versions of software PyTorch 2.13 and Torch AO 0.17. The conversion completely failed because that specific software combination referenced a removed internal code overload,
Yeah.
specifically a function called eton.transpose.dimName.
So an open source developer somewhere removed one highly specific internal function in a software update, and it brought a massive, highly complex AI deployment to a dead stop.
Exactly.
This highlights just how fragile the entire AI ecosystem really is. You can have perfect theoretical math, but if your software dependencies are mismatched by a single version number, the entire system breaks.
It all comes crashing down.
So how did they fix it? Because they didn't just casually patch their live environment.
No, they treated it like a contamination.
Mm.
They completely isolated a brand new, separate CPU environment, literally naming the folder .venviv-e1-ptq.
Unbelievable.
They installed an older, stable version PyTorch 2.11, froze the environment manifest, generated a new SHA-256 hash just to that software environment, and finally proved they could get finite, mathematically converted outputs without the software crashing.
And they applied that same obsessive paranoid control to their calibration data, too. To actually calibrate the quantization process, they couldn't just grab random images from the internet.
Right.
They validated a deterministic data set of exactly 512 unique images from the CFAR10 dataset. And they used a fixed random seed of 2026-0729. They even recorded the exact first 10 index numbers selected by that seed into the logs just to prove to any future auditor that the data cannot be altered or cherry-picked.
This raises an important question for anyone following AI developments today, though.
Yeah.
When you see the constant stream of press releases from tech companies publishing massive breakthroughs in AI efficiency, you really have to ask, how many of them operate with this level of hash-verified, hardware-tested rigor?
Probably very few.
Right. How many claims of, we shrunk our model by 50%, are based entirely on theoretical math on a whiteboard, rather than a frozen deterministic software environment tracking peak VRAM and 95th percentile tail latency?
So what does this all mean? When you look at the hashes, the isolated virtual environments, the exact 11 million parameter counts, it really is like watching scientists operate in a level 4 biological clean room.
That's a perfect comparison.
If one single speck of dust, or in this case one mismatched Git hash or one undocumented PyTorch update, gets into the environment, they consider the entire theoretical claim to be contaminated and ruined.
Completely ruined.
It makes you look at all those flashy tech headlines with a lot more skepticism. If this teacher-healed quantization team is demanding this level of absolute proof just to pass Gate G1 on a relatively small ResNet 18 model, you really have to wonder what massive flaws are hiding in the unverified metrics of much larger commercial models.
Exactly. And that transparency is the core value of this research.
Yeah.
The methodology is just as important as the mechanism of teacher healing itself. They're trying to empirically prove that you can achieve highly capable, highly reliable AI on cheap, low-power devices.
Which would change everything.
It would. If they succeed, if the confidence-aware gates and temperature scaling can actually restore the nuanced capability lost by rounding down to INT8 without destroying the energy and memory gains, it is a massive step toward the true democratization of AI.
We're talking about fundamentally changing how we interact with intelligence. We are talking about bringing powerful diagnostic AI into rural healthcare clinics that, don't have the budget for server racks. We are talking about advanced educational tools in remote areas operating completely offline.
And completely private.
Right, preserving user privacy. Because if the AI fits on your phone, your personal data never has to leave your physical device to be processed in some corporate cloud. It breaks the AI out of the data center.
But that democratization only works if the healing process is mathematically sound and empirically proven against the true deployment reality.
Which leaves us with a really fascinating, somewhat unsettling paradox to think about.
Oh.
Yeah, this entire premise of teacher healing relies on having a massive, capable teacher model. In this specific experiment, it's a ResNet 50 healing a smaller ResNet 18.
Right.
The teacher has to be highly capable, fully calibrated, and running in full FP702 precision on expensive hardware just to provide those perfect gated lessons to the student model.
It requires immense upfront resources to create the efficient outcome.
Exactly. But as the AI industry races toward building models with hundreds of billions or even trillions of parameters, what happens when the teacher models themselves become so incomprehensibly massive and deeply cloud-dependent that a smaller company or a university can't even afford to run the healing process in the first place?
Wow, yeah.
If the only model smart enough to act as the teacher requires $50 million of computing power just to perform the distillation, does the cure eventually become as inaccessible as the disease?
That is a very real possibility.
It's definitely something to chew on as we watch these digital brains get bigger, smarter, and more trapped in the cloud. We want to thank you for taking this deep dive with us into the architecture, the strict mathematics, and the absolute forensic blueprint of efficient AI. Until next time.